We've now looked at the relationship between gravitational potential energy and kinetic energy. We have seen that when gravity is the only force acting on an object, then the work done by gravity causes a change in the kinetic energy. From this, we can define a gravitational potential energy. That potential energy tells us how much work gravity can do, and this is how much kinetic energy an object would get if it fell that distance. This relationship between the work done by a force and kinetic energy is not special to gravity. The work done by all the forces acting on an object must equal the change in kinetic energy. So we can set the net work done equal to all the forces acting on our object. We have a work done by external forces, such as a hand pushing on our object or a rope pulling on our object. We have the work done by non-conservative forces, so W sub nc, and for our case, the main non-conservative force we're going to work with is friction. And the work done by friction is the friction force multiplied by the displacement. We also have the work done by conservative forces, which for our purposes is gravity. So here we will use the change in potential energy times -1 to get the work done by gravity. We will rearrange this to show that the change in kinetic energy plus the change in potential energy plus the work done by friction is equal to the external work done by the object. If no external work is done, then the change in these three very different types of energy all must add up to be 0. This is true no matter how complicated the motion is. As long as there is no external force, the sum of the changes in energy must be 0. Since the sum of the energies must stay the same, it's considered to be a conserved value. This concept is called the conservation of energy, and it applies to all form of energy. So this concept works because of work. The net work on an object is equal to the change in kinetic energy, so the work done by each force is intimately related to the change in kinetic energy. Let's do an example. So a bead on a wire slides down a frictionless wire from a height of 1.2 meters, and then goes through a loop-de-loop with a height of 1 meter. How fast is the bead going at the top of the loop? First, we write down our conservation of energy equation. So the change in kinetic energy plus the change in potential energy, U, plus the work done by friction is equal to the external work done to the bead. The external work here is 0, since there is no external force. The change in kinetic energy is 1/2 mv squared, since the bead is starting from rest. The change in kinetic energy is -1 times mgh, because the bead is going down and losing potential energy. The wire is frictionless, so the friction forces, or the friction work, is set to 0. We have a slight problem because we don't know the mass of the bead. However, if we rearrange the equation, we find that 1/2 mv squared is equal to mgh, so the masses cancel. So 1/2 of v squared is equal to gh. So now we plug in our numbers, and where the distance that the bead only falls is 0.2 meters, since it starts at 1.2 meters, and then it's at 1 meter at the top of the loop. So we do some arithmetic, and we find that the velocity of the bead at the top of the loop here is equal to 2 meters per second. This problem shows us that when we examine some, fiendishly complicated motion, where figuring out and trying to solve the kinematics would be a nightmare, we can examine it using energy conservation to turn the problem into a relatively simple problem. All we need to know here is the change in height, and if we know that, we know the change in kinetic energy, and hence the speed. Now we're going to look at another complicated problem. So two stones are thrown with the same initial speed at the same instant from the top of a roof of a building. One stone is thrown up at an angle of 30 degrees above horizontal, and the other is thrown horizontally. Neglecting air resistance, which statement is true? The question wants to know whether the stones will land at the same time or not, and if the stones will land with the same speed or not. So let's consider the question of speed. Both stones start at exactly the same height, so they most have the same gravitational potential energy. Secondly, they're both thrown at the same speed, so they both have exactly the same kinetic energy. When the two stones land, their potential energy has switched to kinetic energy, and the air resistance is negligible, so the kinetic energy of the two stones is the same. If the kinetic energy is the same, then the speed must be the same. On the issue of when do they land, that depends on the y component of the initial velocity. The stone that is thrown horizontally will land at the same time as if it was dropped. The stone that was thrown at a 30-degree angle has a significant y component, so it's as if you threw it up into the air. When you throw one stone up at the air and drop the other, the drop stone will land first, and the stone that is thrown up into the air will land second. So that gives us our answer, C, where the stones will have the same velocity or the same speed, but they will land at different times. Please note that the horizontally thrown stone will have a much larger x component of the velocity, while the thrown stone will have a larger y component of velocity. But the kinetic energy of the two is exactly the same when they hit the ground. So this is another example of how conservation of energy can simplify a pretty complicated problem. Okay, so it's your turn. I've coded up 2 conceptual problems about conservation of energy, and then in the next video we'll add heat to the mix.